Hey everybody. Today we're doing some applications of the derivative. Really, that's just a math professor way of saying word problems. Regardless of the context, the derivative represents the instantaneous rate of change of a function. So whenever you see the words instantaneous rate of change, you should be thinking about writing down a derivative. Here's a few examples. If s of t is the displacement of a particle, then ds dt, the instantaneous rate of change of displacement with respect to time, is just the instantaneous velocity of the particle. Similarly, the instantaneous rate of change of velocity is going to be the acceleration, and therefore, putting those two ideas together, the second derivative of displacement is going to be acceleration. If C is the concentration of some chemical reactant, then dC dt is the instantaneous rate at which the concentration is changing. If V is the amount of gasoline in a car's tank, then dV dt is the instantaneous rate at which the tank is draining, or I suppose filling up. Finally, if N of t is the population of a large colony of ants, then dN dt is the instantaneous rate of change of the population. Of course, N, the population of ants, is probably going to actually be an integer, but if N is large, we can approximate that function N of t with a continuous one and make sense of the derivative. Let's do a visual example. Here's the graph of the velocity of some particle. We'd like to know, first of all, when the particle is moving forward. So that's going to be the case when velocity is positive, that is, when ds dt is greater than 0. So really here we're asking, where is the graph above the t-axis? That's the case between 0 and 2.5 and between 5 and 8. Secondly, where is the particle standing still? So now I want to know, where is velocity equal to 0? So that's going to be the case between 8 and 10, of course. Notice here also that velocity is equal to 0 at about 2.5 and at about 5. So instantaneously, at least, the particle is also standing still at those values. Next, when is the particle accelerating? Now I'd like to know when velocity is increasing, that is, when dV dt is greater than 0. So on the graph, I'm looking to see where the graph of the velocity has a positive slope. In this case, it's going to be from 0 to 1 and from 4 to 6. Finally, when is the particle's velocity constant? Now I'm asking, where is this graph horizontal? So that's going to be between 3 and 4 and between 8 and 10. One of the most important applications of the derivative is in economics. Suppose we have a cost function, C of x. In other words, C of x is going to represent the total cost for a company to produce x units of some good. The derivative, C prime of x, is just the instantaneous rate of change of the total cost as production increases. Now, since the instantaneous rate of change is approximating the average rate of change over a small interval, C prime can be thought of as the approximate increase in C when x increases by 1. So if x goes up by 1, how much is total cost increasing? Because of that interpretation, the derivative C prime of x often gets called the marginal cost function. Similarly, if we have a revenue function or a profit function, we can define marginal revenue or marginal profit. Let's run through an example using this idea. The cost of producing X dishwashers is given by this cost function, 1800 plus 100x minus 0.1 x squared. We want to find the marginal cost when 100 dishwashers are produced, and then find the actual cost of producing a 101st dishwasher. And then we want to do a couple of questions using average cost. First of all, let's just compute the marginal cost when 100 dishwashers are produced. Here, I take a derivative, I get 100 minus 0.2x. And I can evaluate that at 100 to get the marginal cost when 100 dishwashers are produced. Here, $80. Do we interpret that to mean that the 101st dishwasher is going to cost about $80 to produce? The second part of this problem asks us to find the actual cost of the 101st dishwasher, just by computing directly. So we're going to compute it by taking the total cost of producing 101 dishwashers and subtracting off the total cost of only producing 100. This will be the exact cost of the 101st dishwasher. Plugging into C of X and simplifying a little bit, I get $79.90. Notice how close the exact cost of the 101st dishwasher is to the approximation there in the first part of this question. Also notice that the first part of the question required a lot less work. Next, let's find the average cost per unit when X dishwashers are produced, and then evaluate that for X equals 100. So average cost is going to be total cost divided by the number produced. That is to say, C of X divided by X. We can simplify that a tiny bit to get 1,800 over X plus 100 minus 0.1X. Plugging in 100, we get 108. So when we produce 100 dishwashers, the average cost per dishwasher is $108. Finally, let's get a derivative of C bar of X, plug in 100, and try and get a feel for what that might mean. C bar prime is going to be the derivative of C bar. I'm viewing 1,800 over X as 1,800 times X to the negative first. So the derivative of C bar is negative 1,800 X to the negative second minus 0.1. Plugging in 100 and simplifying a little bit, I get negative 0.28. Remember, a derivative always represents an instantaneous rate of change, and so C bar prime of 100 is going to represent the instantaneous rate of change of average cost at a production level of 100. To say it differently, the average cost per dishwasher when producing 101 units is approximately 28 cents less than the average cost when producing 100 units.